So, thank you for inviting me to speak today. I'm excited to discuss two fascinating fields and explore their intersection. A common question I receive is about the relationship between machine learning and physics, especially astrophysics and cosmology. Although these fields may appear very different at first glance, they share many similarities, particularly in the analytical tools and methods we use today. In fact, even before the recent surge in machine learning, astrophysicists and cosmologists were already employing sophisticated statistical modeling techniques, methods that have now been reframed as machine learning or advanced modeling tools. There's a very direct connection here, and I will explain how our work in cosmology relates to machine learning. Before I dive deeper, let me briefly share my background. I completed my master's from the University of Cambridge after studying at the International Center for Theoretical Physics in Trieste. My journey began in Pakistan. After ICTP, I returned home and taught in Karachi before being fortunate enough to attend Cambridge for Typos Part 3. Then I joined Professor Stephen Hawking's cosmology group at the University of Cambridge, where my direct supervisor was Tobias Beldorf. He was an advanced Stephen Hawking Fellow and Professor Blake Sherwin. After completing my PhD, I was lucky to get a postdoc position at the University of Geneva. After completing my postdoc, I worked in the financial services as a global AI literacy lead and where I design AI and data science courses for thousands of finance professionals. Currently, I'm focusing on my own venture. It's called Chem Adventure. The focus is for AI in education. Enough about my background, and let's start to understand cosmology. Cosmology is the study of the universe as a whole. It's fascinating because it spans an enormous range of scales, from the smallest physical scales, such as the initial conditions at the Big Bang, to the largest structures in the universe. Although we do not fully understand what triggered the Big Bang, we do know that shortly after this event, the universe underwent a phase of accelerated expansion called inflation. This inflationary phase occurred when the universe was roughly 10 to the power minus 34 seconds old, though its exact dynamics remains a mystery. Following inflation, the universe entered a period known as the Dark Ages. Eventually, as the universe emerged from this phase, the first hydrogen atoms was formed and light began to travel freely. This light, which we now detect as the cosmic microwave background radiation, carries imprints from the inflationary period. Even though we cannot observe inflation directly, we can study its physics indirectly through the information preserved in the CMB data. However, interpreting this data is challenging. There are around 200 different models of inflation, and one of our key tasks is to determine which model correctly describes the early universe. Observational evidence suggests that the matter density during inflation was close to a Gaussian distribution. In basic statistics, a Gaussian distribution is completely undescribed by its variance or power spectrum in the terminology of cosmology. If the initial conditions were non Gaussian, it could follow many different forms. Various models of inflation, each driven by different physical processes, can produce different initial conditions for the universe. Thus, by analyzing the CMB data, extracting the signals of inflation, and reconstructing the initial density field, we can potentially determine whether the field was is truly Gaussian or non Gaussian. Any detected non Gaussianity would provide compelling evidence about the physics of inflation. Once light started propagating from the surface of last scattering, when the universe was about 400,000 years old, it embarked on a journey that has lasted nearly 13.6 billion years. Throughout this long journey, light has traversed the evolving universe, observing the formation of structures ranging from galaxies and superclusters down to our own solar system. This light encodes a wealth of information about gravitational redshift, matter evolution, and structure formation. Therefore, even the CMB, which is effectively a two-dimensional image of a three-dimensional universe, contains critical clues about the underlying physics. As gravitational forces caused matter to evolve, the initially simple possible Gaussian conditions evolved into complex structures we see today. We observe the universe through two primary windows, the CMB at the early times and galaxy surveys, which trace how galaxies cluster together across cosmic scales. Understanding these scales is crucial. To put the cosmic scales in perspective, consider that an average human is less than 2 meters tall. The Earth has a diameter of roughly 12,000 kilometers, and our solar system spans several light years. A light year, the distance light travels in 1 year, is vast by comparison. For example, it takes light about 100,000 years to traverse the Milky Way. Nearby galaxies are separated by distances on the order of millions of light years, and the observable universe spans roughly 93 billion light years. On the largest scales, beyond about 100 million light years, we study the clustering of galaxies and galaxy clusters, known as the large scale structure of the universe. In cosmology, we also use units such as megaparsec, where one parsec is approximately 3.2 light years. For example, our Milky Way is about 30 kiloparsecs in diameter, and superclusters are typically about 100 megaparsec. Although we do not observe dark matter directly, simulations reveal that if we could, it would appear as a complex cosmic web. In these simulations, dark matter is distributed into halos, filament, and void. Halos are regions where dark matter clusters densely and galaxies forms within them. Smaller halos contain fewer galaxies, while larger halos can attract and merge with smaller ones. Filaments connect these halos, and voids are nearly empty regions between them. Observationally, we see only the galaxies, the luminous tracers, rather than the dark matter itself. And by studying how galaxies cluster, we can infer the properties of the underlying dark matter distribution and in turn learn about the initial conditions and subsequent evolution of the universe. Our observational tools include the CMB, which provides a two-dimensional snapshot of the early universe, and three-dimensional galaxy surveys. While the CMB offers a relatively clean view with well understood physics, it is limited by its 2D nature and the loss of some information in projection. Galaxy surveys, in contrast, map the three dimensional distribution of galaxies and hold the potential for extracting much more information. However, the galaxy distribution is highly nonlinear due to complex processes like galaxy formation and evolution, making it challenging to model accurately. Because we only have one universe to observe, it is essential to extract as much information as possible from the available data. One promising approach is to combine the complementary information from the CMB and Galaxy surveys through cross correlation techniques, thereby improving the signal to noise ratio. There are three major ongoing and upcoming Galaxy surveys: DAISY, Euclid, and SST, that will provide data on billions of galaxies. Even though these surveys will cover only a fraction of the universe's total galaxy population, the total population is roughly around hundreds of billions of galaxies. We must maximize the extraction of information from the limited dataset. The fundamental challenge for cosmologists is to model and infer the underlying physics from these galaxy surveys. In our work, we start with the observed galaxy map, which gives us the three-dimensional positions and redshifts of galaxies. And then we define something called the summary statistics to capture the key information about the underlying matter distribution. Since we cannot observe dark matter directly, we rely on these summary statistics, such as galaxy clustering correlations, to compare with theoretical models. To model the data, we combine our theoretical understanding with the observational summary statistics. Our theoretical models depend on several parameters, such as the expansion rate, matter density, dark energy properties, or modifications of modifications to gravity. We then perform Bayesian inference to constrain these parameters by comparing the theoretical predictions with the observed data. For example, one common summary statistics in cosmology is the power spectrum, which is equivalent to the 2 point correlation function. More complex statistics include bispectrum, 3 point correlations, and trispectrum, 4 point correlations. Although higher order statistics carry additional information about non Gaussian features, they are computationally much more expensive to calculate. Our current models, for instance, using the effective field theory of large scale structure, are very effective on large and quasi-linear scales, but they face challenges when dealing with the highly non-linear small-scale regime. To give you a sense of the scales involved, large scales refer to structures such as superclusters and the cosmic web. Quasi-linear scales include galaxy clusters, where perturbation theory can be applied with some success. Small scales cover individual galaxies and subclusters where nonlinear effects dominate and our theoretical model becomes less reliable. While we have a solid framework for modeling the linear and quasi-nonlinear regimes, the small scale or highly nonlinear regimes contain a wealth of data that remain challenging to exploit fully. In practice, we must carefully balance the wealth of available small scale information with the limitations of our modeling techniques. Let's discuss how we measure and model these statistics. We observe the galaxy distribution and extract the power spectrum by transforming the spatial density field into Fourier space. In this context, the wave number k represents the Fourier mode. Small k corresponds to large scale features, while large K represents small scale fluctuations. We then define a likelihood function, the probability of observing the data given our theoretical model. Even though the underlying metal density field might be non Gaussian, the central limit theorem justifies approximating the likelihood as Gaussian when summing over many independent Fourier modes. However, when modeling nonlinear scales, the calculation of an accurate covariance matrix becomes more complex and computationally expensive, often requiring high order corrections, for example, one loop, two loop, so on, in perturbation theory. An additional modeling challenge is that we observe galaxies rather than underlying dark matter. This introduces the concept of galaxy bias, the relationship between the distribution of galaxies and dark matter. In my PhD work, I developed an effective field theory based model of galaxy bias, which includes various counterterms and stochastic contributions. These extra parameters must be marginalized over during statistical inference so that we can obtain unbiased constraints on the underlying cosmological parameters. This framework has now become widely used in cosmological survey analysis. So if you model galaxy bias using the effective field theory of large scale structure, you can see for power spectrum at tree level and one loop and bispectrum and trispectrum at each different level, you need to include a lot of bias parameters. And the more number of parameters you add, your model will become complex, and quantifying these bias parameters will be very useful in order to get the non-degenerate and unbiased constraints on your actual cosmological parameters. The technique has been used to analyze galaxy surveys, and this is the result from one of the recent papers where the authors used the power spectrum analysis using the effective field theory method, marginalizing over these nuance parameters to get the constraints on the cosmological parameters. Despite the success of these analytical methods, there remain tensions in cosmological measurements. For example, the so called Hubble tension refers to statistically significant discrepancy between the Hubble parameter measured from early time probes like the CMB and late time observations such as galaxy clustering. This tension might indicate that our current models are incomplete and that new physics, for example, evolving dark energy or alternative models of dark matter, could be at play. Okay, so the constraints we obtain from traditional analysis, such as those based on power spectrum, bispectrum, and other summary statistics, are useful, but they leave some tensions in cosmology unresolved. One critical issue is that our final parameter estimates depend strongly on the statistical inference method we use, particularly on the specification of the data model's likelihood function and the priors. So, if the model or the likelihood function is not exact, the inferred parameters can be biased. In our work, the parameters we aim to constrain, for example, those related to matter density and amplitude of fluctuations or matter energy properties, are crucial for understanding the underlying physics. Even a small bias introduced by an incorrect likelihood function can lead us to misinterpret the fundamental physics. Although a Gaussian likelihood is often used as an approximation justified by the central limit theorem when averaging over many modes, there are many circumstances where this approximation fails. In nonlinear regimes, or when the underlying density field is non Gaussian, to obtain unbiased and reliable constraints, we need an approach that allows us to work with the exact or at least a much closer approximation of the likelihood function. So, how do we arrive at a more accurate non Gaussian and generic likelihood function? This is statistically very challenging because the exact likelihood of our high dimensional nonlinear data is often intractable. However, advances in machine learning offer promising solutions through simulation based inference, or SBI. With today's computational power, thanks to GPUs and efficient algorithms, we can now build highly realistic simulations that start from the initial conditions of the universe and incorporate all relevant systematic effects, generating hundreds of thousands of simulated data realizations that mimic the actual observation. For example, the galaxy surveys, we can effectively learn the true underlying probability distribution. This simulation based approach enables us to bypass some of the approximation inherent in traditional likelihood constructions and to capture the full complexity of the data. In effect, we use these simulations to calibrate our inference machinery so that we recover the correct posterior distributions over our parameters when applying Bayes' theorem. Let's talk about the Bayes' theorem and understand the posterior likelihood and prior. Bayes' theorem is given by this formula. The first term, probability of theta given the data, is the parameter distribution given the data, likely defined by the probability of x given your model. There are two broad strategies for improving our statistical inference when the standard likelihood method is insufficient. One is the data driven likelihood. In this approach, one directly learns the likelihood function from the data or from simulations. This method can capture non Gaussian features and complex correlations that are missed by simple analytical models. Second method are generative methods. Modern advancements in machine learning, especially in the area of generative modeling, offer another pathway. Unlike predictive models that simply output point estimates or classifications, generative models learn to sample from the underlying data distribution. In other words, they learn the full probability distribution P of data given theta from which one can generate realistic synthetic observations. Common generative models include autoregressive models, variational autoencoders VAEs, and particularly promising for our application, normalizing flows. Normalizing flows work by starting with a simple distribution such as a Gaussian and then applying a series of invertible transformations. These transformations wrap the simple distribution into one that closely matches the complex distribution of the observed data. More advanced models like diffusion models also show promise in capturing intricate details of the data distribution. In cosmology, these generative models can be applied to learn the distribution of the underlying density field from simulations. Once the generative model is trained, we can sample from it to approximate the true likelihood function or to perform direct posterior inference. So here we will show a result from this paper. It's a forward modeling approach to analyzing galaxy clustering with simulation-based inference of galaxies. To illustrate, let me describe one project where we employed these ideas. We generated our we generated around 20,000 highly realistic simulated galaxy surveys using forward modeling. So forward modeling means you model the initial conditions, you model the final galaxy distribution from the initial conditions. So from initial conditions of the universe all the way to the observed galaxy distribution. With these simulations in hand, we apply an autoregressive normalizing flow model. The idea here is straightforward. So you start from the initial conditions, you obtain the nonlinear matter field using the numerical methods and body simulations. So n-body simulations can take you from the initial conditions to the nonlinear dark matter. From nonlinear dark matter, you apply something called the halo finder to find out the distribution of dark matter halos. Once you have the distribution of dark matter halos, you apply halo occupation distribution to get the number of or the clusters of galaxies within these halos. And after that, you apply galaxy masks or all the systematics of a particular galaxy survey to obtain the data of which mimics the actual galaxy surveys. With these simulations in hand, we apply an autoregressive normalizing flow model. The idea here is straightforward. So start simple. Begin with a simple known distribution, typically a Gaussian distribution, and then you learn the transformation. Use a series of invertible differentiable transformations to morph the simple distribution into one that accurately reflects the complex observed distribution of galaxy density. By training this model on our simulated data, we directly learn the posterior distribution of the cosmological parameters. When we compare these results to traditional perturbative methods, we find that the normalizing flow approach can yield constraints that are up to 27% time tighter. So this is particularly for sigma 8. So in further word, by doing the field level based inference, of course using convolutional neural networks to compress and process the data, we achieve even more impressive results, up to twice as tighter as our analytical results. In practical terms, these improvements are equivalent to obtaining data from a galaxy survey that is 60% time larger, a significant benefit given the high cost associated with such surveys. So, in summary, we face a fundamental challenge in cosmology. Accurately inferring key parameters from observational data requires a robust, unbiased likelihood function. Traditional Gaussian approximations are not always sufficient, especially in the presence of nonlinearity and non Gaussian features. Simulation based inference using generative models provides a powerful alternative. By leveraging advanced machine learning techniques such as normalizing flow, we can learn the true underlying distribution of the data and thereby obtain much tighter and much more reliable constraints on cosmological parameters. This approach not only improves our current analysis, but also the potential to resolve lingering tensions in cosmological measurements by making full case by making full use of the complex information encoded in galaxy surveys. Thanks for watching, and if you have any questions, please do send me your comments. Thank you.